Welcome to Operations Research. Today, we are diving into the fascinating world of rectangular games. Imagine two rival ice cream vendors on a beach, where every customer one vendor gains is a customer the other vendor loses. This is a strict head-to-head competition. We will learn how to mathematically model these highly competitive situations, predict opponent behavior, and find the absolute best strategy to guarantee success. Let us get started. Now that we have introduced the idea of strict competition, let us define what a rectangular game actually is. In academic terms, we call this a two-person zero-sum game. Why zero-sum? Because if you add the winner's positive points and the loser's negative points, the total is always exactly zero. There is no win-win outcome here. We assume both players are perfectly rational, meaning they both want the absolute best possible outcome for themselves. They also make their choices simultaneously, without knowing what the other person is doing. This creates a fascinating dynamic where you must anticipate your opponent's moves. To understand how these rational players make decisions, we need a way to organize their choices. We use a mathematical table called a payoff matrix. Think of this as a rectangular grid of numbers. The rows represent all the possible strategies available to the first player, and the columns represent the strategies for the second player. The number located at the exact intersection of a row and a column is the payoff. Because the game is strictly zero-sum, whatever the first player wins, the second player must lose. Therefore, we only need to write down the first player's winnings in the grid. Building on this grid concept, let us look at the formal mathematical notation. The capital letter A represents the entire payoff matrix as a whole. Inside this matrix, the symbol A sub ij represents the individual number located at the ith row and jth column. The index I represents the first player's choices, and the index j represents the second player's choices. If this number is positive, it means the first player gains that amount and the second player loses it. If it is negative, the first player loses that amount, meaning the second player actually wins it. Understanding this notation is crucial for our next steps. With our matrix set up, we must ask, how do players actually choose their moves? Both players are highly pessimistic. The first player assumes the second player will always try to force the worst possible outcome. So the first player looks at the absolute worst case scenario for every row and chooses the row that gives the highest value among these worst cases. This cautious approach is called the maximum principle. The second player is equally pessimistic, looking at the maximum possible losses in each column and choosing the column that gives the lowest value. This is the minimax principle, which minimizes their maximum possible loss. This brings us to the most important equation in rectangular games. The left side of this equation represents the maximum value for the first player. It mathematically states that we first find the minimum value in each row and then find the maximum of those minimums. The right side represents the minimax value for the second player, finding the maximum in each column, then the minimum of those maximums. When these two values are perfectly equal, we call that shared number V, which stands for the value of the game. If this equality holds true, the game has a saddle point, meaning both players will confidently play exactly one strategy. To truly grasp why we call this a saddle point, let us look at its geometric shape. Just like the center of a horse saddle, the red point you see is the lowest part of the curve when you look from front to back, representing the minimum of a row. But simultaneously, it is the highest part of the curve when you look from side to side, representing the maximum of a column. This unique geometric property is what creates the unbreakable stability of the pure strategy equilibrium. Neither player can improve their outcome by changing their mind alone. Now that we understand the theory, let us see this with a concrete example. We have a simple payoff matrix where player 1 has 3 strategies and player 2 has 2. We will apply the maximum principle first. For row 1, the possible payoffs are 15 and 2. The minimum is 2. For row 2, the payoffs are 7 and 5, so the minimum is 5. For row 3, the payoffs are 6 and 4, making the minimum 4. Player 1 wants the absolute best of these worst case scenarios. The highest guaranteed value among 2, 5 and 4 is 5. This is our maximum. Continuing with our example, we now switch to player 2's perspective. Player 2 wants to minimize their losses. In the first column, the possible losses are 15, 7 and 6. The absolute worst case loss here is 15. In the second column, the possible losses are 2, 5 and 4. The worst case loss here is 5. Player 2 compares these worst case scenarios, 15 and 5, and wants to minimize this maximum loss. They choose the smallest number, which is 5. This gives us our minimax value. Finally, we compare the results from both players to find our solution. We compare player 1's maximum value of 5 with player 2's minimax value, which is also 5. Because these two values match perfectly, we have successfully found a saddle point at row 2 and column 2. The value of the game is 5. Physically, this means player 1 should always play strategy 2. Player 2 should always play strategy 2, and player 1 will consistently win 5 units. This is a perfectly stable, pure strategy equilibrium. Let us apply these principles to a real-world business scenario. Two competing coffee shops, Shop A and Shop B, are deciding on their daily special. Shop A chooses pastries, Shop B chooses beverages. We start by finding the worst-case scenario for Shop A's profits. If they choose muffins in row 1, the minimum value is -1, a potential loss. For bagels in row 2, the minimum profit is 5. For croissants in row 3, the minimum is -2. Shop A wants to maximize their safety, so they pick the largest of these minimums. The maximum profit is 5. Moving forward, we analyze the game from Shop B's perspective. Shop B wants to minimize Shop A's profit. Looking at the first column for coffee, the maximum possible profit for Shop A is 6. In the second column for tea, the highest number is 7. In the third column for juice, the maximum value is 5. Shop B compares these worst-case scenarios, 6, 7 and 5. To minimize this maximum profit, they select the smallest number. The minimum of these maximums is 5, which is our minimax value. Now we bring it all together for the coffee shops. We compare Shop A's maximum value of 5 and Shop B's minimax value of 5. Both values are exactly equal, which means a saddle point exists at row 2 and column 3. Shop A should always serve bagels and Shop B should always serve juice. This pure strategy equilibrium guarantees Shop A a profit of $50 since the matrix is in tens of dollars, and Shop B successfully prevents them from making any more than that. Having solved these matrices, you might wonder why this mathematical analysis matters in the real world. Rectangular games form the absolute foundation of game theory, which is used everywhere, from global economics to military strategy. In business, companies use these exact models to decide pricing strategies, knowing full well their competitors will react aggressively. In cybersecurity, defenders use game theory to anticipate the worst-case attacks from hackers and allocate their firewalls accordingly. By finding the saddle point, we replace blind guessing with a mathematically guaranteed safety net. We have covered a lot of ground today, so let us review the key takeaways. First, a rectangular game models a strict competition where one person's gain is exactly the other person's loss. Second, we use a payoff matrix to neatly organize all possible outcomes based on the strategies chosen by both sides. Finally, by applying the pessimistic maximin and minimax principles, players can find a safe, stable strategy called a saddle point. You now have the mathematical tools to analyze strict competition and find the optimal move without hesitation. Great work today.